Hello everyone, this is Yatisha Rajanala and I am going to present my final project presentation titled Prediction of Diabetes Mellitus using Data Mining Techniques. In the present scenario of tackling diabetes, predictive models stand as a vital tool offering early detection and personalized interventions. According to the World Health Organization, statistical analysis show that diabetes affects over 400 million people worldwide, with projections estimating a rise to 700 million by 2045. However, predictive models offer hope amidst these staggering figures, enabling targeted interventions that can prevent or delay the onset of diabetes, improve patient outcomes, and reduce healthcare costs. Thus, this project is a simple sample for such large-scale datasets. Using this project as a tool, we can aim to develop a predictive model to forecast the occurrence of diabetes mellitus. This approach integrates key parameters such as age, body mass index, and HbA1c levels alongside indicators of other chronic diseases to enhance the accuracy of predictions. Through meticulous pre-processing of the data, including handling missing values, encoding categorical variables, and standardizing numerical features, the robustness and reliability of the model can be ensured. Furthermore, the project delves into healthcare data mining techniques, evaluating their efficacy and applicability in predicting diabetes mellitus. By summarizing the results of this analysis, we can understand the methodology of predictive modeling in healthcare. For this project, the USA Chronic Diseases Indicators CDI dataset available through healthdata.gov was used. This dataset offers a comprehensive repository of information on various chronic diseases, including diabetes mellitus. From this resource, relevant features like age, BMI, and indicators of other chronic diseases were extracted, enabling the construction of a robust predictive model. In predictive modeling, data preprocessing is pivotal for accurate model development. For this project, the dataset was imported into Python with subsequent selection of relevant columns such as gender, age, BMI, and specific chronic diseases. This streamlined the dataset, enhancing the predictive power of the model while reducing computational complexity. The categorical variables were handled, including the initialization of encoding functions post multicollinearity assessment, which ensured model integrity by mitigating the risk of distorted coefficients due to multicollinearity. The missing values were addressed to fortify dataset reliability, and finally, the process CSV file was saved. Thus, these pre-processing steps collectively refined the dataset, laid a sturdy foundation for accurate and reliable predictive models in the project. This is the Python code that I had used for data pre-processing, which includes all the steps as mentioned earlier. You can take a look at it. In predictive analysis, the dependent variable represents the outcome being predicted, which is diabetes in the case of this project. Independent variables, on the other hand, are the factors influencing the dependent variable. These are the variables of gender, age, hypertension, heart disease, smoking history, and all the other variables as mentioned in the table. Now, after the data cleaning, the next step is moving on to the analysis part. For the analysis of the dataset, Weka was used, which is a popular suite of machine learning software tools used for data mining tasks. It was developed at the University of Waikato in New Zealand and stands for Waikato Environment of Knowledge Analysis. After loading the dataset into Weka, the relevant attributes were selected, such as selecting diabetes as the class assigner for analysis and changing the numerical data to nominal data types. Furthermore, the data mining techniques suitable for analysis were selected, and the data sets were prepared into testing and training sets. For this project specifically, the classifier methods of naive Bayes method and J48 decision tree were performed. This is a working summary of the naive Bayes classifier method. As seen in the image, this model exhibits high accuracy and recall rates, suggesting strong performance in the classified instances. In the second model, the J48 decision tree model demonstrates a less balanced performance across multiple metrics, including precision and recall, but shows well accuracy within the correctly classified parameters, suggesting lower false positive rates. Both the J48 decision tree and the naive Bayes models demonstrated similar overall accuracy in classifying instances of diabetes mellitus. However, their performance varied across different evaluation metrics. The J48 model achieved perfect classification for one class, but failed to classify any instances for the other class, indicating limitations in capturing the underlying patterns for that class. Conversely, the naive Bayes model exhibited a more balanced classification for both classes, but had a higher overall error rate compared to J48, suggesting potential accuracy trade-offs. Despite the potential errors, the naive Bayes model demonstrated a balanced classification, effectively predicting instances across different categories. With higher overall accuracy and consistency in performance, the model showcased proficiency in leveraging the available data for informed predictions. Though it is simple, its speed offered a computationally effective framework for both training and inference processes. This straightforward approach is particularly beneficial in real-time or resource-constrained settings, and thus these aspects of the naive Bayes model had collectively positioned it as the optimal choice for predicting instances of diabetes mellitus. As we have reached the end of my project presentation, I would like to share all the new techniques that I have learned along the way during the predictive analysis of these models and their interpretations. I have become more skilled in using Python to prepare data for analysis, handle missing values, and standardize the features. Additionally, I have learned to utilize Weka for evaluating models and gained a deeper understanding of the importance of data preprocessing in predictive analysis. I can now interpret model results confidently and choose the most appropriate models for specific predictive tasks. Thus, utilizing these skills, I can now help healthcare professionals with making informed decisions and drive effective analysis processes in the future. Now, as we conclude, this is about the project that I had done, and these are the references for it. Thank you for your time, and I hope that this presentation has reflected the data mining techniques that I had used in the most accurate way. Thank you.